Hello, Code Monkeys. Today we are going to talk about the main sorting loop of our HeapSort algorithm that we were working on yesterday. So let's get our handy dandy picture of our heap up there. I'm getting a little bit better at drawing silly little rectangles. How fun is that? So, with what we accomplished yesterday, we can ensure that this is the biggest number up here, and the numbers get smaller as we go this way. It will be a valid heap. So, how do we turn that back into a sorted array? Well, the answer is actually quite a bit simpler than I thought it was when I first started working on this. So what we're going to do is we're going to take our biggest number here, and we are going to go ahead and stuff it into the last element of the array. So that's going to go over here in box number 6. And when we do that, keep in mind that these are the same data structure here. We are also going to take the last element of the array, this box, for they are one and the same, and it's going to be a swap. So once we do that, we actually have one of the smallest numbers up at the top in the root node, as they call it. And our biggest number is actually down over here. That's our biggest number. And this is a small number. So what do we do about that? Well, the first thing we're going to do is we're just going to pretend that this box here is not part of our heap anymore. And then we're going to use some very simple rules. We're actually going to use the same rules we used way back several videos ago to assert the heap integrity of each individual node to propagate this small number back down the heap. And once we have gotten it all the way back down the heap, I shouldn't say all the way back down. Once we've gotten it to a point where it doesn't propagate anymore, the heap integrity at that point will be reasserted. So, how are we going to do that? We're going to do it with nested for loops. We're going to do everything with nested for loops. That's not a strong statement. So, we have our heap again, with a small number up top, and some other numbers over here. What is our outer loop going to look like? Well, our outer loop is going to be the loop that does this over and over until everything's sorted. So that's actually fairly easy to determine the bounds of. Start with I equals... Actually, let me back this up a step. Because we actually, above this, will just include in our little diagram of pseudocode, swap h sub 0, and then we want to swap it with the last element of the heap, which is going to be h sub end minus 1. And then, because we have already processed the first or the last or the largest element, we can actually start I at 1 here. Very, very crafty. And then I is going to end at that's going to have to be less than something. We'll come back to that. And I believe all we want to do here is have a typical increment. Alright, inner for loop. Inner for loop, we are going to, this is going to be the one where we propagate our small element back down the heap. So, I start j at 0, because that is our root node. And j is going to need to stay less than or equal to LNL, the last non-leaf node of end, but then we have to remember to subtract I, because our heap is actually getting smaller every time we iterate through this outer loop. And how are we going to update j? Well, j is going to chase our small number down the heap. But it's actually easier if we don't do that in our loop bounds up here. So we can actually just leave that slot empty. Now, j is ultimately going to be equal to, oh, how do we want to do this? It's going to be, it's LGN. Oh, if I remember how I wrote this, it's going to be H, comma, J, comma, end. And we're going to use our handy-dandy C trinary operator, which I don't actually think I've gone over before, but it works a lot like an if statement. So if we're swapping left, we're going to make j equal to L of j. And if we're not swapping left, we're going to check and see if we swap right. RGN of H, comma, J, comma, end. And then if we swap right, it's going to be R of J, and I've run out of room. Let's cram it in over here. And if it's not that, then we're just going to make j end. So that is how j is going to update. It's going to be end if we didn't discover anything to swap to. So I believe at this point we can say something like if j equal end, we can break and then we don't actually have to worry about an else because the else is implied when we have a break statement like that. We will swap H sub j, I always want to say that wrong, and H sub parent of j. Because remember, we already updated j here. That's going to need a semicolon too. Now, why don't we update j here like we normally do? It is because that always happens at the bottom of the loop, and I am trying to remember why that doesn't work for us. It doesn't work for us because you can put it in there, I think you just end up rerunning checks twice, is the short answer. Anywho, back to the loop. When we are all done with this, those are my curly braces. We're actually going to have another swap here. And we're going to go ahead and swap h of 0, or h sub 0, with h sub end minus 1 minus I. Remember, heap is getting smaller each time. And I can just about fit my semicolon in there. Hurrah! Wow, that is not a very good square brace. So essentially, what we're going to do is we got a small number up there, and it's going to propagate down the heap. Once it does, we know we have heap integrity reestablished. We know that this will once again be the biggest. Oh, that's not how you spell biggest. Ho ho. This will once again be the biggest. There we go. And we can pull our funny trick where we send this then, once again, to the very end of the data structure. Remember, this is in fact an array. 3, 4, 5, 6, and 7. So every time we reassert the integrity of the heap, this is going to be our largest. And we can swap this repeatedly with successive ends as we shrink the data structure. We don't actually shrink the data structure, but we're shrinking the part of it we're paying attention to. And so on and so forth like that. All right, I think it's time to get some code up in here. How are we doing on time? 13 minutes, we can at least get started. I like to keep these at about 20. I do actually have to show you guys the code, though. Isn't that wild? Okay, camera looks alright. Nano. HeapSort.c. That's where we're going. Okay. We already have our enforce heap function. Very important. And we already tested it and made sure it worked. Assuming our test worked. Always possible to bungle things. So, what do we do next? We need a name. That's what we need. Let's call it heap ops. And I think what we will do, I was going to take an unsigned int star named h. It's going to take a, we just need the end, right? Yeah. Unsigned int end. Return 0 if you work correctly. Alright, int I, comma, j. Our outer loop. I equals 1. And then I needs to be less than, I believe we would just run this all the way to end. I guess we didn't actually go back and do that. Let me check the blackboard real quick. Oh yeah, we never did go back and do that. Well, we're going to run it to end. And we'll increment it one at a time because that makes sense for what we're doing. Do I actually have the swap function written out? I sure do. Okay. We are going to swap h sub 0 and h sub end minus 1 minus I. Hurrah. Ho 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 ho. This isn't JavaScript, you can't just do that. And we need an inner for loop, j equals 0. J needs to be less than. This is where we start getting tricky. That end minus 1 minus I is going to come up a lot. J is going to be less than. How about the parent? Well, LNL end minus I should do the trick. Less than or equal to. It can in fact be the last non-leaf node. And then we will close that off there. I believe we're going to need braces for this one too. Now, let us... We can do this as an if tree, or we can do it the funky way we did on the blackboard. How did we do it up here? Up here we use the normal if tree. Okay, let's keep doing that then. If LGN, that's what we called it. If LGN h comma j comma end, then we are going to yes, we use a lot of braces doing it this way. That's okay. J equals L of J. I can actually do this in the other order. Makes it a little easier to conceptualize. Pass your conceptualization checks, Harry Dubois. Swap, what is it? H sub j and h sub L of j. Yes. That's how we do these things. Oopsie, else if, two words, RGN, H, J, comma end. Oopsie, needed. Gotta actually close your parentheses, folks. That's what you get for working in Nano. And here we are going to swap H. How are we doing on time? Oh, rolling right up on it. I think we'll break the video before we test. That should be fine. H sub R of J. That should be fine. J equals R of J. And then, I think at this point, we can just do else break. So this should be very similar logic to what we saw on the blackboard. It's a little easier to troubleshoot if you actually write out the if tree, kind of spreads things out in a way that makes them easier to catch errors. And let's, yeah, we're right up on 20 minutes. We'll compile this and make sure it compiles. And then we'll break the video and we'll test it next time. -o, heapsort.o, heapsort.c. Hey, it worked! Alright, hope everybody's learning a lot here. If you stick around when I start the next video, you will see the thrilling conclusion. And the thrilling conclusion is, amazingly, a lot of me pulling my hair out. Have an excellent rest of your day, folks.